In this e-content, we are going to see a small note about iron values and its properties. So we'll see what do we mean by a characteristic polynomial, characteristic equation, iron value and an iron vector. So we will consider a matrix which is of order n cross n over a field F. Let I be a unit matrix of the same order and let X be any non-zero column vector. Then determinant A minus lambda I gives us the characteristic polynomial. If we equate the value of determinant A minus lambda I is equal to 0, we will get the characteristic equation of the matrix A. And if we find the roots of the equation, determinant A minus lambda I is equal to 0, we will get the iron values of the matrix A. If we are given an equation, Ax is equal to lambda x, it can be written as A minus lambda I into x is equal to 0. So if we are able to find a value for x other than 0, then the values of x is said to be an iron vector corresponding to the iron value lambda. There are a few properties of iron values which are very useful in solving numerical problems. So the first property is, if we are having an n cross n matrix, then we will have n iron values. From fundamental theorem of algebra, an equation of nth degree will have n roots. So suppose our characteristic equation is of nth degree, then it will have n roots. So thereby a n cross n matrix will have a characteristic equation of nth degree and it will have n iron values. So for this I will consider a 2 by 2 matrix. So we should have a characteristic equation of order 2 and we should have 2 iron values. So over here I written the characteristic equation and I am getting a quadratic equation and we have got 2 iron values, lambda equal to 1 and lambda is equal to 5. So over here the order of the matrix is 2, the characteristic equation is of order 2 and we are having 2 roots. Therefore a n cross n matrix has n iron values. Property 2. Sum of the iron values is nothing but it is the trace of the matrix. Trace of the matrix is sum of the diagonal elements. So here also I am taking a 2 cross 2 matrix. Say 1, 2 and in the second row you are having the entries as 1 and 1. So over here the sum of the diagonal elements is 2. So now I have got to form a characteristic equation and determine iron values. So here I am getting a quadratic equation, lambda squared minus 2 lambda minus 1 is equal to 0 and the iron values are 1 and 1. So sum of the iron values is 2 and the sum of the diagonal elements are also 2. So therefore the sum of the iron values is equal to the trace of the matrix. Property 3. Product of iron values is equal to determinant of the matrix. So again I have a 2 by 2 matrix, 1, 4, 2 and 3. So the determinant value is nothing but 3 minus 8 which is 5. So again I have got to find the characteristic equation and determine the iron values. So the iron values are here minus 1 and 5 whose product is again equal to minus 5. Hence product of the iron values is equal to determinant of the matrix. Then property 4. If one of the iron values is 0, then the given matrix should be a singular matrix or its determinant value should be 0. And the converse part is also true. If at all one of the iron values is 0, then the determinant value should be equal to 0. So I will consider a 3 by 3 matrix. Its determinant value is given by 0. Then the characteristic equation is a cubic equation and the roots are lambda, lambda minus 3, lambda minus 15 is equal to 0. So over here the iron values are lambda is equal to 0, lambda is equal to 3 and lambda is equal to 50. So over here one of the eigenvalues is 0 and the determinant value is also 0. So if the determinant is 0, one of the eigenvalues is 0. If one of the eigenvalues is 0, naturally the determinant value will be 0 or the given matrix will be a singular matrix. Property 5. The eigenvalues of a triangular matrix are the diagonal matrix. So over here I'll consider a lower triangular matrix. The eigenvalues are nothing but 1, 3 and 5. And we have got to evaluate and show that the eigenvalues are 1, 3 and 5. So over here once again the factors of the characteristic equation are 1 minus lambda, 3 minus lambda and 5 minus lambda is equal to 0. So the eigenvalues are 1, 3 and 5. And the diagonal elements are also 1, 3 and 5. So the eigenvalues of a triangular matrix are the diagonal elements. So one of the most important properties, if the eigenvalues of a matrix A is lambda and if you are performing any operation on the matrix A, the same operation also has to be performed on the eigenvalue lambda. Say if A is a 3 cross 3 matrix with the eigenvalues 1, 2 and 3. And if f of A is given as matrix A squared, we are squaring the matrix. So in this case, the same operation has to be performed on the eigenvalues. They should be squared. So the eigenvalues will be 1 squared, 2 squared and 3 squared. If f of A is equal to A cubed plus 2y. So in this case, the eigenvalues will be 1 cubed plus 2. Similarly 2 cubed plus 2 and 3 cubed plus 2. So over here, in this example, f of A is given by e power A and the value of A is given as matrix 0, 0, 1, 0, 0, 2, 0, 0, 0. So this is an upper triangular matrix. So the diagonal elements are 0, 0, 0. The eigenvalues are 0, 0, 0. So the eigenvalues of the matrix are 0, 0, 0. And the given function is f of A is e power A. So I have got to perform an operation for the function f of A is equal to e power A. So I will have e power 0, again e power 0, e power 0. So which is 1, 1, 1. So this is a very simple way to determine the eigenvalues. So these properties are very important in solving numerical problems. Thank you.